All right, my friends, let's take a look. So the basis step is so basic that sometimes it just looks really redundant. But basically what you're saying is that if n was 1, so if n up here was 1, first of all, on the term by term side, that would just be the 1. And then on the formula side, that would be 1 squared. Okay, so you're basically showing that the terms that you'd get when n is 1, which on the left side would just be 1, you're showing that that would also equal what you'd get on the formula side, which in this case would be 1 squared. And so you could see that this is obviously true. And so in this case, that would be what it looks like to complete the basis steps. So again, you're going to show what happens when you have a partial sum on the term by term side for just the first partial sum, and then you show that on the formula side you get the same answer. Okay, so that's that. Okay, so we just showed on our theoretical ladder, we just showed you can get to the first rung of the ladder. Okay, now for the inductive step, you are going to assume that the claim is true for some arbitrary constant k. And so this is what that looks like. So you would say assume that 1 plus 3 plus 5 plus 7 plus, and then if this right here, my friends, at the top here, if this is the definition of the nth term, if that's what this is, then the kth term would just be exactly that, but with a k instead of an n. So 2k minus 1. Okay, so the assumption is that that would indeed equal this right side with k in for n. So this is our assumption. Okay, and this is the part that looks a bit like circular reasoning, where all we did was replace the n's with k's, but because n means every natural number out there and k is just a certain one, it is actually not circular reasoning. Okay, so we're going to assume that, so here's what we've done. We've said assume that you can get your foot on some kth rung of the ladder. Okay, now the burden of proof is in the next part. So we're basically going to show that if our assumption holds true, that you could get to the next rung of the ladder. So, so basically what we want to show, we wish to show, oops, there, that, oh my goodness, I'm having a hard time writing. Our claim also holds true for n equaling k plus 1. Okay, so let's get started on that. So what would the sum of the first k plus 1 terms be? Well, it would still have 1 and 3 and 5 and 7. And it would still have the kth term, 2k minus 1. It would just also have the k plus 1 term, which you could find by taking this right here and replacing n with k plus 1 and then simplifying it. So I'm going to show, I'll show the pre-simplified version. That would be 2 times k plus 1 minus 1. Okay, now a note so that you know what our goal is, okay? So our goal for this part is to show that what we have here, s sub k plus 1, and we have the term by term stuff. Our goal is to show that it would equal this formula side, but instead of n, it should say k plus 1. So we're basically trying to show that all this term by term stuff adds up to k plus 1 quantity squared. And if we can get it to look like that using our assumption, then we will have finished our proof. So to do that, you always start with what I have here, the expanded term by term piece. And then what you do is you can always use your assumption. And so what was our assumption? Our assumption was you could replace the first k plus 1 terms with k squared. And so we're going to take exactly that piece of it and replace it with k squared. But then you also have this little extra k plus 1 term there. So there we go. And then next to that step where you used that assumption and you did that substitution, we're going to say by our assumption. Okay. Now all we have to do is simplify this, and we're hoping to make it look like this k plus 1 quantity squared. So let's simplify it. So we'd have k squared plus, I'm going to distribute the 2 in. We'd have 2k plus 2 minus 1. From there, we'll have k squared plus 2k plus 1. And then you could factor that down as k plus 1 quantity squared. Oh, man. And we did it. Okay, so what did we just accomplish? We basically showed that your claim was true when n, we're going to go back to the ladder up here. We showed that your claim was true when n equals 1. We showed that assuming that you can get to the kth rung of the ladder, then you can always get to the k plus 1 rung on the ladder. And by creating that loop, we basically showed that if n equals 1, then because of this loop that we created, that means n equals 2 would follow, n equals 3 would follow, n equals 4, 5, 6, all the way up. Whoa, I just lost half my letter. All the way up to infinity. And so we just showed that the claim is true for all n values for every natural number ever. Okay, and that is what an outline looks like for a proof of by mathematical induction. Here we go. Okay. You know what's funny is that is really repetitive. That's exactly what we just did. But maybe let's show it, let's just kind of show the shorter version, because I kind of show the words and then how you do it. So let's just kind of show what would it look like if you're asked to prove something like this by mathematical induction. So the first thing you do is your basis step. So that would mean if n was 1, that would yield s sub 1. On the term by term side would be 1. And then on the formula side, that would be 1 squared. And so you just passed your basis step. Then for your inductive step, you assume that there exists some value k from the set of the natural numbers such that our claim holds true. That is that s sub k, which term by term would equal 1 plus 3 plus 5, all the way up to 2k minus 1, that is indeed equal to k squared. So that's your assumption, right? Okay. Now that you've got your assumption, now all we must show is that our claim also holds true for n equaling k plus 1. Okay, so let's get started on that. So what would s sub k plus 1 be on the term by term side? It would be 1 plus 3 plus 5 plus, it would still have the kth term in there. It would just also have the k plus 1 term in there. So that's the term by term side. And remember, this is something that you either scratch it out on the side or you think in your head. Our goal is to show that we could get this, just using your assumption, our goal is to show that we could get basically k plus 1 squared on the right side. So, okay. So next thing, use your assumption. We can substitute all the way from that first term to the kth term. We can substitute that out for k squared. And then you just have to bring your k plus 1 term down. Remember to say by our assumption. There we go. Simplify it. You'll have k squared plus 2k plus 2 minus 1, which is equal to k squared plus 2k plus 1, which is equal to k plus 1 quantity squared. And at that point, you've completed your inductive step. Okay. And so then your conclusion would be, therefore, S sub n, which was defined as 1 plus 3 plus 5 all the way up to 2n minus 1, is indeed equal to n squared for all n from the set of the natural numbers. And we did that by mathematical induction. I'll just write a little. There we go. And at the end of a proof, it's very common is to end it by writing either QED, or another common thing would be to just put in a little filled in box to show that you finished your proof. There we go, my friends. That's what the full thing looks like. Okay. So for the next part, we're going to consider example 3 here. So prove that the S sub n, defined term by term as 3 plus 11 plus 9 all the way up to the quantity 8n minus 5, could be found instead by doing n times the quantity 4n minus 1, and that would be true for all n from the set of the natural numbers. And it's implied that you're going to prove this by mathematical induction. All right, see how it goes. Check in with me in the next video. Good luck.